Hi everyone. In this video our objective is to address old Regents questions that are related to types of chemical reactions. Question 1. Which two solutions, when mixed together, will undergo a double replacement reaction and form a white solid substance? So they're looking for a precipitate that will form. And another key that they tell me is that we have two solutions, meaning that both of these reactants, in a sense, are soluble in water. Our first task is to actually perform the double replacement, meaning we're going to take this sodium and replace it with lithium and write down what the products might be. So here they are. Those would be the potential products for the reaction between sodium chloride and lithium nitrate. Now, to investigate this further, we are looking for something that was soluble, these were soluble, and now a substance that is no longer soluble. And we have a table that will assist us with that, and here it is. So let's investigate sodium nitrate. On this left side, we see that we have all of these substances that are soluble in water. So substances that have in their formula group 1 ions such as lithium, sodium, and so forth, they will be soluble in water unless these exceptions are met. Now, there are no exceptions. So anything that has lithium, sodium, or so forth in the formula will be soluble in water. So here we have sodium nitrate, and it fits this rule perfectly. This will be soluble in water. So this is soluble in water. I'm only crossing it out because I'm looking for one that becomes insoluble. Now here we have lithium chloride, and again, lithium, when combined with anything else, is soluble. So both of those would be soluble in water. Double replacement reaction is not occurring there. This next one, when we replace the potassium with the silver, we end up with potassium nitrate and silver chloride. So potassium again is a group 1 element. So potassium will be soluble. Now what about the silver nitrate? I'm sorry, the silver chloride. Well, it doesn't affect this rule. Let me look at the others. Oh, a chlorine. Alright, so all formulas that have chlorine in it are soluble. So those substances would be soluble unless they have these with them. And here we have silver. So silver with chlorine, it's insoluble. It would become a precipitate, a solid. That is our answer. But let me also just, for completeness' sake, uncover what the other substances would be. On your own right now, pause, reflect on this table, and confirm that all of these other substances right here would also be soluble in water. Number 2, which equation represents a double replacement reaction? So we just have to inspect this for two substances that will switch, in essence, switch their dates. So here we have sodium with water, and now we have sodium hydroxide and just hydrogen. We're not seeing two replacements. Here we have calcium, what is that? That's calcium, what's CO3? Carbonate. All right. We have calcium carbonate, and then it becomes calcium oxide and carbon dioxide. I do not see double replacement. In fact, I see this one substance breaking up into two. This would actually be a decomposition. Here I have lithium hydroxide and HCl. If dissolved in water, it's called hydrochloric acid. The lithium is now with the chlorine, and this hydrogen is now with the hydroxide. That's looking good. And this last one, well, oxygen isn't paired with anything, so it doesn't have anything to switch with. So the answer is, in fact, C. And let me uncover this so that you can see it a little bit more clearly. Pause and reflect on this. This is showing you that the lithium is taking the place of the hydrogen, while the hydrogen is taking the place of the lithium to become these products. Number 3, given the balanced equation representing two chemical reactions. Here we have 1 mole of chlorine with 2 moles of sodium bromide, yielding 2 moles of sodium chloride and 1 mole of bromine. Here we have 2 moles of sodium chloride yielding 2 moles of sodium and 1 mole of chlorine. Which type of chemical reactions are present in these equations? I do notice while inspecting here that the chlorine is taking the place of bromine. I'm sorry, the chlorine, yes, that's right. And the bromine is now free and uncombined. In this next one, I see that sodium chloride is breaking up into 2 separate substances. Now, what does that mean? It means we definitely have a single replacement reaction in the first one. And, well, it is a decomposition in the second one. It is choice A. Number 4, given the balanced equation representing a reaction, we have zinc, that's a solid, combining with H2SO4, which is, when aqueous, that's sulfuric acid, yielding zinc sulfate and hydrogen gas. Which type of reaction is represented here? Now, I do notice that neither of the two products is a solid, so right off the bat I know it's not a double replacement. And a synthesis would have to be when we have 2 separate substances like this, yielding 1 substance, so it is not synthesis. A decomposition would be the opposite of that, so it is not a decomposition. In fact, it is a single replacement. Let me show you where that's occurring. The zinc is taking the place of the hydrogen, and the hydrogen is now cast aside. And here it is. So the answer is C. Number 5. In which type of reaction do 2 or more substances combine, that's the operative word, to produce a single substance? That's also an operative word. So we're looking for a situation where we might have A plus B yielding AB. And when does that happen? Synthesis reaction. Number 6. Which balanced equation represents a chemical change? Now, this is an oldie but goodie type of question. It's back to our first unit, actually our second. So we are looking for a chemical change. Here we have water as a liquid combining with energy, becoming a gas. That's physical only. Here we have a liquid becoming a gas. Wait, but that's a gas of hydrogen. It was water. Now, gas of hydrogen and a gas of oxygen. Do we see a change in substances? 100% we do, and that would be a chemical change. Let's just inspect the other two. Here we have a liquid, water, becoming a solid water when it loses energy. That's like when you put it in the freezer. That's only physical. And here we have gas of water becoming liquid when it loses energy. That's like when the steam in your shower hits your mirror and it cools down and it becomes a liquid again, but this time found on your mirror. So it is neither C nor D. As a confirmation, the choice is B. Alright, number 7. Given the equation, we have 1 mole of iodine combining with another mole of iodine, becoming a 1 mole of an iodine molecule. You see we have 2 iodines now chemically combined. And we have this existence of some form of energy to the total of 35 kilocalories of energy. Now, the energy is located on the product side. That's important to keep in mind. This equation shows that the formation of an iodine molecule is what? Now, again, it's on the product side. So this energy right here must have originated from here and is now given off and needs to be represented because we have this thing called law of conservation of energy. So energy needs to be identified if it's either being absorbed or released due to a chemical reaction. So here this energy is being released. It is no longer part of this iodine and this iodine. And that is actually also consistent with our studies on bond formation, because when bonds form, energy is released, and that takes on this term called exothermic. So Is it exothermic because energy is being absorbed or energy is being released? And it's number B, letter B. So what would a question look like if it was an endothermic reaction? So let's just put here A plus B yields AB. Now, if it required the input of energy to make happen, well, then this reaction would have to absorb energy. And let's just say we put 35 kilocalories on this side. Well, that would be saying that in order to make this reaction occur, A and B needed to absorb 35 kilocalories of energy so that it got recombined and reformulated into the substance now known as AB. This would be an endothermic reaction. All right, I'm going to show you on the next slide a table that will also assist periodically. So here we have table I. Table I is the heat of reactions at 101.3 kilopascal, a measure of pressure, and 298 Kelvin. So all of these different reactions are taking place in an environment with this level of pressure and this temperature. Now the keys here are to look at delta H, which is measured in kilojoules, so delta H, change in heat, a measure of energy in essence, and right down here, a legend on the bottom that talks about delta H, and this minus sign. A minus sign indicates an exothermic reaction. So at times during some questions, chemistry questions, they will display for you a different reactions. And one of those reactions might be one of these depicted on table I. And it might ask you if it's endothermic or exothermic and not even show you within the equation where the energy is, if it's on the product side or on the reactant side. So we have to investigate this. And if you see a negative sign, it means it's an exothermic reaction, meaning that the energy would be written on the product side. So 890.4 kilojoules would be written on the right side with the products, whereas right down here, this reaction could be written as 182.6 kilojoules plus nitrogen gas plus O2 gas, and I'll put the yield side going down because I'm running out of room, will yield 2 moles of nitrogen oxide. And this depicts that it is an endothermic reaction because it's on the reactant side. So keep table I in mind when it comes to endothermic and exothermic questions.